Okay. Well, hello everybody. Welcome to this great green energy series. Thanks for joining us at 10 in the morning on a Saturday. Um, this green energy series, we're going to be talking about energy efficiency and PV sizing. And you'll know much more about kind of what that's about as we jump into slides. A little plug for Solar Oregon. Solar Oregon has been around for getting close to 40 years. We are a nonprofit, and we're the organization's goal is to do education outreach regarding solar and to help homeowners in the community adopt solar and navigate the solar policies and how to accelerate the adoption of solar in Oregon and Washington. You can use this link to support our work. We're a small nonprofit. We're very lean and mean. A lot of the work is done on volunteer time, but we do have a small budget to hire a skeleton crew that does more than their fair share of work. And then some of the programs we provide do incur a little bit of cost, and so it'll be helpful if you help donate to this cause. And then in terms of navigating the Zoom, feel free to use the chat and the Q&A to provide questions, and we'll get to them at the end. A little bit about me. My name is Edward Louie. In my day job, I work at Pacific Northwest National Laboratory as a building energy efficiency research engineer. Outside of work, I love cycling, archery, and then a big project that I'm constantly working on finishing is to build an off-grid, all-electric heat pump everything, the solar-powered tiny house. A little disclaimer, the views in this presentation do not necessarily represent Pacific Northwest National Laboratory, the U.S. Department of Energy, or Solar Oregon. I've made best efforts to convey facts and information accurately. However, you're encouraged to do your own research and calculations before making any investment decisions. All right, so in terms of this PV and energy efficiency, we're going to look at a few different scenarios here. We're going to start with the idea of taking a fairly inefficient home. We're going to look at what happens when you switch the gas equipment, in this case, a gas furnace, being the main gas consuming piece of appliance, to a heat pump. What does that do to efficiency? What does that do to energy? And then what happens to the home's energy when you start upgrading the enclosure? We're going to start with looking at the attic, then the crawl space, then the ducts. Then we're going to go to wall insulation and then the windows. And we're going to look at PV sizing as these changes get made and what it looks like. So the work we're doing here is let's see if we can hide. Yeah. Okay, so the baseline home we're looking at is located in Portland, Oregon. It's a 2,000 square foot single story house, 3 bedrooms, 2 baths, fairly non-special house. It's fairly old, so we're gonna assign it an air leakage that's quite leaky, 15 air changes per hour. But you think, wow, okay, 15 air changes per hour. So like the entire interior volume of air in this home is replaced 15 times per hour. That's a lot, right? Well, it is, but that 15 only happens in a standard, what's it called, a blower door test, where the house is pressurized to 50 pascals with respect to the outside to kind of have a standard pressure difference. And then using that standard pressure difference, that's how the ACH, or air changes per hour, is measured. So, on a day on a regular day in your home, you're not really replacing that much air that often, but it's a standard way to measure how leaky a building is. And so this whole air changes per hour at 50 Pascal is kind of the standard. And 15 is fairly typical, believe it or not. I mean, it sounds like a lot, but it's fairly typical of old homes that have not been air sealed or insulated in any way. And then the walls, we're looking at 2x4, 16-inch on center, uninsulated wall cavities with OSB sheathing on the outside and wood siding. The attic, we're looking at a baseline that does have some insulation in attic, R13. This is a vented attic. We're assuming a home with a crawl space, and that in this case, that crawl space is uninsulated and it's vented. The windows, we're starting with a baseline assumption of clear glass, double pane, non-metal frame, air-filled windows. We're assuming a ducts that are fairly leaky at 20% duct leakage, insulated to R4, located in the crawl space. I've done a lot of duct leakage testing in homes, and I will say in older homes, 20% is sadly a fairly common reality. It has a 13-SEER single-stage air conditioner, a gas furnace that's 80% efficient, water heater that's electric, but it's not heat pump. It's only an electric resistance, your standard electric resistance water heater, 95 UEF, 50 gallon. We are assuming 100% LED lighting. That is maybe not 100% a great assumption. Maybe most people are like 80, 90%, but it's not too much of a stretch to be at 100%. Given the low cost of LED lighting available today and the wide number of options. LED lighting is one of the great success stories of energy efficiency. It works really well, it's long lasting, and adoption curve has been very good. We assume an electric clothes dryer and electric cooking range. So as you can see, the only appliance that's gas here is the furnace. And so one of the first things we're going to look at is what happens when you switch from a gas furnace to a heat pump. One thing that I think doesn't get really talked about when you switch from a gas furnace to a heat pump, even a very efficient heat pump, in this case, we're picking in this model a 22 SEER 10 HSPF variable speed heat pump. So it's not top of the line, but it is in that top like 10 to 15% of available product SKUs in terms of performance. So it's really good. We're also switching from a electric resistance water heater to a heat pump water heater that helps reduce energy the consumption on the water heating side. But even so, it is a huge change when you go from a gas furnace to a electric heat pump in terms of your energy consumption, and especially in January and December. This curve will look a lot more at this curve and the ramifications of this curve in later slides. But you're thinking about like an electric bill that's $120 and then like doubling that electric. So it's not surprise if you do this furnace to heat pump conversion and then end up in December, January getting a $200+ electric bill. I've in my home, I've seen electric bills are as high as like 230. So anyways, that's despite the high electric cost, you think that, okay, well, what's going on if the electric bill more than doubled in December and January? Like, is the home actually more efficient? And believe it or not, the answer is yes. That the amount of energy, because it's a heat pumps are appliances that move heat rather than creating heat. And even in December and January, they have a coefficient of performance. So basically, the amount of electricity you give it versus the amount of heat it can deliver, it's more than one. So it can, for 1 unit of electricity you give that heat pump, it can move 2.5, 3 units of heat. And so that efficiency of being able to move heat, not create heat, which is something that a gas furnace can never do, contributes to the efficiency of heat pumps. And so you can see in this boxed part of the table, just by switching from a gas furnace to electric heat pump, we dropped the energy use of the home quite a bit, even though what happened is that we increased the electricity usage by a lot. But when you're looking at just the electricity graphs, what you're not seeing is, well, you eliminated gas, and the amount of gas you eliminated is quite a bit. So if you just switch from, if you have a fairly old home with, a fairly inefficient enclosure, we saw that the amount of electricity you're going to use goes up by a huge amount, especially in December, January. So now we're going to look at, okay, well, what happens when you start making your building enclosure more efficient by adding insulation and air sealing to keep the warm air that you spent lots of money heating from escaping through the cracks. And so one of the best bang for the buck and first things you do is to work on your attic and to improve the air sealing and insulation of your attic. Why is that? Well, it's because warm air is less dense, so it pushes up against the ceiling, and then it finds every single crack and hole in the ceiling and escapes through those holes into lower pressure outdoor environments. Just thermodynamics and fluid dynamics 101. Warm air is less dense, and so it floats to the top of your ceiling and finds the cracks. So air sealing the attic, the ceiling attic interface is really important, yields a lot of savings. And then also, because your attic ceiling plane is the warmest, then it makes sense to improve the insulation there the most. And so in this case, we upgrade it to R49 in the modeling. And then attic air sealing we're assuming it can reduce the air leakage of the home from 15 ACH 50 to 10. That is a very achievable amount of air leakage reduction. One thing that you're going to find with paying money to improve the enclosure of your home is that you're never going to get to zero. There's no such thing as a hermetically sealed, airtight home. Even Passive House has a standard of 0.6 ACH 50, and that's extremely difficult to achieve. And it's a very low number. A code-built home in Oregon today, theoretically, needs to achieve 3 ACH 50, but they have provisions to allow up to 5 ACH 50. So in the 3 to 5 range is what a brand new home built to all the modern energy codes is today. And if you can achieve upgrading your home to an ACH 50 about like 8 or 7, that's considered really good. So we'll continue to look at those scenarios. So okay, so once the attic has been air sealed and insulated, the next logical spot to then work on is that crawl space. Especially in this case, the crawl space doesn't have insulation, and so we upgrade it to R19. We upgraded the duct insulation from an R4 to an R8. Duct insulation makes a big difference because in the wintertime, when you're running that heat pump, the air flowing through those ducts is 110 degrees. And so that's a really big temperature difference between that 110 degree air and the outside, which might be like 40 degrees. And so improving that insulation value of that duct, especially if it's in unconditioned space like in a crawl space, makes a big difference. And then we reduced the duct leakage from 20% to 8% by sealing the cracks and the seams of the ducts. And so these efforts will reduce the whole house air leakage. In this case, we assume it went from a 10 to down to an 8. And so you can see that, we're dropping those lines. And so this U-shaped curve that started out being really dramatic is now flattening as we do these upgrades. And that's really good for solar, because we'll get to that. Next scenario that we looked at in this graph is to look at what happens when you drill holes in the wall to blow in cellulose. In this case, the walls were originally uninsulated, and now they're filled with R13 insulation. And so that dropped the line some more. And then lastly, we looked at window upgrades. What happens if you upgrade your windows, in this case, going from that clear glass double pane window to triple pane windows that are filled with argon. They have low E coatings in order to achieve a much lower U value and solar heat gain, so much more insulating windows than before. And then these efforts reduce the air leakage from an 8 down to a 7. Interestingly, when you use computer modeling software, if you just improve the windows, that change in selecting the different windows from before and after, it never considers a change in the air leakage. So the air leakage reduction effects of new windows is not factored in. And so the only way you can factor that in is by actually also going to a different area in computer modeling where you can select the whole house air leakage value. And so in order to account for that, we reduced the air leakage from an 8 to a 7 to help include that aspect of window upgrades into the model. And it really doesn't make that much of a difference. And I think the window modeling aspect of computer models is one area that is the most poorly, I guess, like contrived part of a computer model that does building energy modeling. Field testing has found, customers find and notice a much bigger difference from window upgrades than computer modeling suggests. And I think one of the things that computer models don't consider is really the massive improvement in comfort near windows when you upgrade to much higher performance windows, because when you're standing near a window or sleeping near a window, you really feel more comfortable because that window is now much more insulating. And so the radiative warmth from your skin doesn't get sucked out through the window in the wintertime. And then by warming that window surface, you also have a major reduction in that convective breeze shown in the GIF animation that happens around the window. And so these comfort improvements aren't really always captured in energy models. So that's that. And so let's do a little double check to make sure, okay, these computer modeled 2,000 square foot home, like, are these U-shaped curves, are they realistic? Well, we have an example home. It happens to be my home. I've upgraded every piece of gas appliance to heat pumps or electric. And so, I've got a few years now of all electricity usage data. And again, it's a very U-shaped curve. This home is originally built in 1892. It's fairly leaky. It has some insulation in the attic, some insulation in the walls. And this insulation obviously was added after 1892. This home has had a modge podge of upgrades and remodels throughout its lifetime. And so now it has some insulation attic, some insulation in the walls. It still doesn't have very much insulation or any insulation in the crawl space. It has clear glass, double pane, aluminum windows. This home doesn't actually have ducts, and so it's actually heated and cooled with ductless heat pumps. It has a heat pump water heater, ventless heat pump dryer, induction range. And then one of the unusual things about this home is that it's not that uniformly conditioned. There's only about 1,000 square feet of conditioned area. The other 1,000 square foot is semi-conditioned. So it's a little bit of a wonky example. But again, it shows this U-shaped curve, which is very typical of all-electric heat pump homes. So we're confirming that our modeled shapes of electricity consumption is accurate. And this type of kind of U-shaped curve it has been identified in the electricity and energy efficiency literature. And it's been coined the Falcon curve because of how U-shaped it is. And it's a load shape that is extremely worrisome to grid planners, utility planners, utility modelers, because they're very concerned because our electric grid is not currently capable of delivering that much electricity in to meet the demands of January and December. And this is a hugely different curve than our current electricity demand curve. Our current electricity demand curve is much more like that black line in this graph. It's fairly flat, and most grids have a small summer peak somewhere around July, August from air conditioning usage, and maybe a little bit higher electricity usage in December, January, because people are maybe taking longer baths in order to warm up during those cold winter days, and maybe supplementing their central heat with some electric blankets and a little bit of space heating here and there. But really, because much of the space heating is still predominantly natural gas, electric utilities are not seeing a major winter peak. But if we start to improve efficiency by switching to heat pumps, that really, really changes the electric load curve. And the question right now is like, okay, if this is our scenario, because we do want to utilize that huge decrease in energy usage and major increase in efficiency by switching to a heat pump, but we also need to figure out how to avoid this really, really steep U-shaped curve. Then it behooves us to do all these what's it called, building enclosure upgrades to really flatten this U-shaped curve as much as possible, in order to avoid needing to spend trillions of dollars to build out bigger transmission and distribution lines, upgrading transformers, and building out lots of electric generating power plants that are dispatchables that operate on natural gas mostly, in order to meet the demands of the electricity demands in January and December. And we can do that by improving our enclosures, and so then therefore flatten out that U-shaped curve. So where does this whole PV element fit in? Well, PV is it's an interesting thing. As you can see in this graph, the peak generation for a PV system is obviously during the summer. But if we switch to heat pumps, really in particularly Portland, I mean, this graph might look slightly different if we were modeling Phoenix, Arizona, but hopefully no one has to live there. It's just too hot. But in a heating dominant climate like Portland, Oregon, we have this conundrum where like the electricity generation is in the summertime, but if you have an all-electric home where it's heat pump for your heat, the dominant energy consumption is in the winter. And currently there's no good way to shift the energy and store the energy from the summer and take it over to the wintertime. The electric utility, such as Pacific Power and Portland General Electric, allows you to do something called net metering, which is an actuarial or accounting way to be able to take those credits from the summertime and use it in the wintertime, which is very generous and nice of them, because electricity has to be generated and used and matched up pretty much instantaneously on a second by second level. There's not really very many good ways to store electricity, especially store it over the course of months, not like days. Batteries are good for storing electricity, to be able to use it across hours and maybe a few days. But when you're talking months, it doesn't work. And so the fact that you're able to do net metering right now and be able to get a credit for generation during the summer months and be able to use it in the wintertime is very generous. It's kind of like, it would be very generous to be able to somehow magically store watermelons that are excess watermelons produced in July, and then somehow preserve that watermelon so that we can sell it back to you in December, January at the same price and availability as July. No one can figure out how to do that with watermelons, and nobody can really know how to do that with electricity either. So that's why net metering at a retail 1-to-1 ratio is a real generous thing that may not last that long, because the logic of it doesn't really pan out. So this is the issue with PV, and so how do we avoid building out that transmission grid and those power plants that cost trillions of dollars to do if we are going to do PV? And one way to do that is to design PV systems that are oversized so that they generate more kilowatt hours than the home needs all year, just so that we can gain some more generation in the winter months in order to meet the load. And so the orange line at the very bottom, that's a PV system sized to be able to net meter zero for a solar year. So and that system is about 8.3 kilowatt system. And in order to really kind of optimize generation, the tilt is around 30 degrees. But when you want a winter optimized PV system, you actually want to tilt that PV system quite a bit more, because the winter sun is lower in the sky. And so by tilting it steeper, you're better able to capture energy during the early spring, late fall season by having a steeper PV system. And so we looked at scenarios like, okay, well, if you were to cover your energy usage all the way through November and starting in February, what size PV system you would need? Well, you would need a PV system that's not quite double, but close to double the size of one that's net metered annually in order to cover the November and February months. And so then that takes us to the red curve here. So you can see in month 2 where, the generation and the demands is about equal, and then same thing over here in November. But a 15 kW system is still not able to cover January and December's energy consumption. As you can see, consumption's higher and generation's lower. Same thing over here in December. And so, there's 43% of the energy required in January that's not met by this 15 kW solar system, and then about 50% in December. And so if you look at the kilowatt hours not covered, that represents, a little bit over 1,000 kilowatt hours. And the, one question is, okay, well, if we were to self-supply this and not need, a multi-million-dollar central generating facility that Portland General Electric or Pacific Power needs to build, if we were to kind of provide this energy ourselves with a generator, how many gallons of gas would you need? And the answer to that, in order to supply about, that 1100, 1200 kilowatt hours, you would need about 157 gallons of gas for a Honda generator to generate that, 1100, 1200 kilowatt hours. That's a lot of gallons of gas. And so, it's also a good visual indicator of what we don't see when we buy electricity from the grid. Just how much energy that is, because it's invisible, it comes through the wires, and it's always available. So like we don't really think about it. But when you model it and do the calculations to be able to visualize it, 157 gallons, like I don't even know that I use 157 gallons of gas in the whole year to fuel my Prius. And so then what will it take to in terms of PV systems to cover both December and January? Well, you need about a 30 kilowatt system, and that's a really big system, and that results in massive amounts of overgeneration for all the other months, just to be able to in December be able to meet the electricity demands. And this demand curve, note, is the lowest one in this graph. So you even when you have a good envelope or a building enclosure with insulation in the walls, the crawl space, you've air sealed and improved your windows and stuff like that, you still need a 30 kilowatt PV system that's tilted for winter optimization if you want to cover December energy consumption. So it's a little bit unrealistic for anybody to buy a 30 kilowatt PV system. 15 kilowatt is actually quite doable. So let's look at how big is a 15 kilowatt PV system. You need about 33 panels, and that 33 panels will take about 38 by 20 foot piece of roof or backyard space if you're going to ground mount it. Go look at a previous green energy series for solar beyond the roof, for all the different ideas on how to mount solar panels if you don't want to put it on the roof. There's lots of different ideas. If you do want to put it on the roof and it needs to be tilted to a winter steeper pitch, a lot of roofs in homes are not that steeply pitched. It's 65 degrees is fairly steep. So if you were to if you were to design a house from scratch that has that steeply pitched roof, what would that house look like? Especially if you want to design it so that it's got a big surface area to mount solar panels on the roof. Well, you might build like an A-frame house. And aesthetically, it's a debate whether this is an aesthetically pleasing house design. But that's an idea, for be able to meet this target of a big roof that is steeply pitched for winter, and be able to mount the solar panels on a roof. I honestly don't think these homes look ugly. I think they're quite pretty. It will look a little odd in the neighborhood. And so and then let's look at cost. And so a 15 kW PV system, I estimate that it will cost around $46,000. It's not cheap, but if you want to step up to a 30, or what will it take if you didn't upgrade your enclosure and you just electrified? So then now you're back to this this orange curve here, this really steep U-shaped curve, and you needed to meet December, January loads with your PV system. How big would it need? And I calculated that you need a 52 kilowatt system, which is just humongous. That 52 kilowatt system would cost around $113,000, so an insane amount of money. And there's the differences there between the different PV systems. Enclosure upgrades are much more reasonable. And the other thing about enclosure upgrades is that you can do it piece by piece. So you can do the attic one year, then do the crawl space the next year, and do wall insulation the third year, so on and so forth. It doesn't need to be all done at the same time. And the total with the enclosure upgrades around $18,000 $37,000. And so just by, dropping that enclosure, like I said, if you didn't do any enclosure upgrades, you would need a 52 kilowatt system. And then, as I said, for the same apples comparison, you need a 30 kilowatt system. So the difference of $37,000. If you just did the walls, you're at 18. So, that's fairly good savings. It's a lot cheaper to do an enclosure upgrade than to install a 52 kilowatt system. Windows, like I said, is a bit of an anomaly. Windows are quite expensive and yield very little, according to the energy model savings. But the comfort, it's very difficult to value, comfort if it doesn't show up on an energy model. But I mean, people don't necessarily, value their kitchen countertop upgrades or their bathroom remodel. And so, economics only gets you so far. Comfort is sometimes a difficult to it's a very intangible thing that to put into numbers. But that's what kind of the numbers look like. And then if you were to install a 15 kilowatt system or a 30 kilowatt system, what do you do with that excess generation? Certainly, you're not going to be able to net meter this system. These oversized systems, like no electric company will allow you to install a system like this and net meter. But it is possible to sign up, instead of for net metering, to sign up as a renewable energy small qualifying facility. This qualifying facility is essentially what you're signing up for is you're signing up as a power plant. And so then you sell energy back to the utility, not at retail rates, because power plants don't sell energy to the grid at retail rates. They sell it at generation rates. And that's typically around 5 cents a kilowatt hour. So, much less than, the 13 cents that you get for retail generation. But besides that, though, it is possible in the future, and I'll show you in a future slide, that you're not always going to get even 5 cents, because if we have lots of solar panels generating tons of excess electricity in the summertime, it may depress the grid to the point that the electric utility has to start curtailing and refusing to buy kilowatt hours generated from solar in order to keep other resources at least spinning at a minimum rate. And so sometimes you might get $0 if selling this excess kilowatt hours in the summertime back to the grid. And so one of the things perhaps you can do is, I don't know, sell it to your neighbor and have a little meter to meter the electric vehicle charging, so that you can bill your neighbor for charging their electric vehicle off of your excess solar. Or it's just you can just value at zero and just donate that electricity to your neighbors and have them charge their electric vehicle for free in the summertime. There's also the possibility of seasonal energy thermal energy storage in the future, and heat pumps that can capture the excess air conditioning and also some excess outdoor heat from in the summertime and store in in-ground swimming pools or underground rainwater tanks. And then by storing this heat underground, it's protected from the air temperature fluctuations, and then in the wintertime be able to grab that heat and really help reduce the energy usage required in December and January. That technology is available today, but it's for sure getting more mature each year. Kind of another thing that can be thought about is can electric utilities kind of do the economic analysis where the excess kilowatt hours you're selling to the grid is specifically purchased by food processing facilities that are doing canning, freezing, drying of fruits and vegetables. And it's one of those like, can a virtual net metering agreement be done between a pool of residential customers and a specific food processing facility? That's just an interesting kind of thought experiment, because fruits and vegetables are much more available in the summertime. That's when most of them are being produced, and we can't possibly as a society eat all those fruits and vegetables in their fresh state in the summertime. Farmers produce way more than the consumption base can ever eat in the summer. So a lot of it goes to canning, freezing, and drying, so that they can be preserved and we can continue to enjoy those fruits and vegetables into the wintertime. But these facilities use a huge amount of electricity, $800 million worth, and this is a figure from like 2008. So I mean, it's probably even higher today. So can that be a way to use excess generation? That's an interesting thought experiment. So I guess in conclusion, like the electrification of like heating is really important for decarbonization. We saw in that table just how much just electrifying the gas furnace does in terms of reducing energy usage, and then by extension, reduction in carbon emission. But it does result in a very significant change in when the building uses energy, and it creates substantially increases in winter peak electricity demands. And those demands will cost trillions of dollars for the grid to upgrade distribution lines, transmission lines, transformers, and power plants, increasing the number of power plants in order to just meet the electricity demands in December, January. And then the rest of the year, they're just sitting idle. So that's not a really good resource where you're only using it 2 months out of the year. And so we've definitely looked at that, the envelope or enclosure energy efficiency upgrades, like improving the air sealing and insulation of a home, it does a huge amount to reduce the amount of winter energy needed, particularly in November, December, January, and February months. And this winter energy reduction is really significant. As you can see in this graph, we reduced it by 1,000 kilowatt hours in December, January. That's a huge amount of electricity to decrease. And then ultimately, if you didn't do these enclosure upgrades and you just looked at the orange line and you had to size a PV system to cover that energy usage in December, January, like you said, you need like a 50 to 54 kilowatt PV system that cost well over $100,000. And then the other question is, even with if you filled your entire roof and your entire yard with solar panels, it just won't fit. So there's also a bit of a logistical space constraint that like makes that scenario not possible. But with the enclosure upgrades, you can then reduce the size of your PV system down to like 15 and maybe 30, 15 to 30 kilowatt, which can fit on a well-designed house that's optimal for winter PV, or you utilize a piece of your property that's beyond the roof, maybe a carport, a driveway, a front yard or backyard that has good solar windows. Then you don't really need to buy any kilowatt hours from the grid, even December, January. And then, as I said, with a 15 kW system, you certainly need to buy, about 1,100 kilowatt hours in December, January. But the rest of the year, you're okay. And that's, be able to, just that 15 kW alone will, help the electric utility out a lot, because they're not having to build, anywhere near as much generating capacity and need to upgrade the transformers nearly as much as if you had like no PV system or a really small PV system that does only annual net zero energy, like an 8 kilowatt system, where you're requiring a huge amount of kilowatt hours to be purchased in the winter months. And so another conclusion is that like we all need to, as solar PV aficionados, really understand this Falcon curve problem and start planning out how to reduce it using enclosure efficiency upgrades to prevent the huge problem of needing to build out a grid that is only utilized for December, January to be able to transmit and distribute that huge amount of electricity needed in December, January, and then also building out, tons of extra dispatchable natural gas power plants that are only really needed in December and January. This is a problem that lots of really smart people that are grid reliability modelers and grid folks are looking at. Here's a slide from the New England independent system operators. So independent system operators are grid operators. They manage the grid. These ISOs are bodies responsible for communicating with all the different generating facilities, whether it be Bonneville Power for the hydropower, to all the different solar farms and wind farms. They do power management to make sure that the right generating units are generating the right amount of power to meet demands, and that the different transmission lines and distribution systems and stuff are all like not overloaded. And these modelers that work for these ISOs are very concerned about the future where we have homes switching from natural gas to heat pumps, and then causing unprecedented, is what they're calling it, future load shapes, which is the Falcon curve, and certain days in the winter when the electric demands are just way higher than we've ever needed from the electric grid. And so that's a huge problem. But then kind of alluding back to how like in certain times we need to value grid excess generation from PV sent back to the grid at $0. This ISO in this slide deck, if you look at the lower graph here for April, there's certain periods when they're called min generation. So essentially what that means is that if you want a natural gas power plant to be able to start up at a moment's notice, you need to operate that natural gas power plant at a certain minimum generation. You can't completely turn it off, because it actually takes hours to turn on even the fastest power plants. And then there are power plants that are not fast that take days to start up. And so you can't just turn it completely dead off. You need to maintain them at minimum generation. And then if these dispatchable power plants are operating minimum generation, they're outputting a certain amount of electricity still. And so they need to be prioritized. And then therefore, when those are prioritized, then perhaps your solar that you're trying to sell back to the grid needs to be deprioritized. And therefore, there's a curtailment, or so therefore you're not allowed to send that excess kilowatt hours of solar back to the grid in order to maintain grid stability. And so another kind of main conclusion is that there are simple solutions to really solving and flattening this U-shaped Falcon curve, and it's really to deal with it has to do with combining PV with enclosure upgrades with heat pumps in order to kind of create that really great combination where we flatten down this U-shaped curve, and then we're designing a PV system that meets more of our winter loads by having steeply pitched solar panels, and it being oversized to meet most of the winter loads. And then next Green Energy series in September, I want to talk about kind of that emerging tech in seasonal thermal energy storage. And here is some of the options that are out there. They essentially utilize a below grade or buried thermal source, whether that be the dirt in the lower left-hand corner, or a tank or body of water, which would come in the form of a rainwater collection tank or an in-ground swimming pool. These are all really good methods where the right two methods are ones where they perform dual purpose. And so, like, people put in-ground swimming pools, not necessarily specifically for seasonal thermal energy storage. People put them in to enjoy the swimming pool during the summer. But if it can provide additional benefits beyond summer leisure, but also be able to help keep your house warm in December, January, that's an excellent additional benefit. And then same thing with the rainwater collection tank. People don't necessarily install those for seasonal thermal energy storage. They install them so that they have some free water to use during the summertime to water, plants and in their garden, and then also to manage stormwater in the wintertime. Those are all, really important needs. But if you can add an additional benefits of be able to help keep your house warm in December, January, that's another great addition. And so then, then with those scenarios, you can, spread out the cost of the seasonal thermal energy storage, not just to being dedicated to just heating the house, but, it's like, well, you just need to look at the incremental cost of upgrading the in-ground swimming pool and upgrading the rainwater collection tank to be able to interface with the heating system of the house or the heat pump of the house, rather than the full cost of installing an in-ground swimming pool, because people already have that there, or they already decided they want to put an in-ground swimming pool. So what's the incremental cost? Versus on the left-hand side, that ground source heat exchanger shown in that rendering, that is a dedicated thermal heat exchanger. So, like, what other use are you going to do? What other use is there to justify digging up the backyard to put in this slinky of pipe to do this in-ground exchange? Well, there is no other justification. So therefore, the full cost of the backyard excavation would have to be placed to installing this ground source heat exchanger, which is a fairly high cost. And so we'll look at kind of these different options, the economics, and how would you actually be able to do it practically.
So Edward, this is a great talk. There are a few questions. There's one in the Q&A and a few in the chat, and you've got like 5 minutes. I think you can do it.
Okay, let's do the Q&A. What do wind generation curves look like year-round? Is there a peak in the winter? Wind generation curves are kind of all over the map. In fact, one expert that at work that I talked to, he said that with solar, we have 90+% accuracy in being able to forecast how much solar we would be able to generate up to like 3 or 4 days ahead. So, like, the forecast is quite good for solar. But with wind generation, we're lucky to be able to get a 30-minute forecast that's more than 90% accurate. And so there is certainly like some kind of knowledge on when it would be windy from a seasonal perspective, but there's also a major kind of short-term problem of how do we predict wind from an hour-to-hour basis, because we're not very good at that, actually. So that's a really interesting thing that I did not know about wind until recently, is just the difference between forecastability of wind generation versus solar PV. Okay, chat. Okay, let's maybe go up to the top. Share slides after the meeting. Yes, we can email out the slides, and then we'll also this recording will be available on YouTube. Source for the program to analyze all these efficiency measurements. Yes, so this is a software called BOPT, and it's available for free by anyone. And it's a computer building energy modeling software that the U.S. Department of Energy spent a great deal of money investing over many years so that it's to get it to the level of like user reliability and ease of use that it is today. Explain what source and site energy are in your charts. Okay, so let's go back to that chart there. This chart. So source energy is the energy that the power plant or the distribution pipeline for natural gas needed to expend in order to get that energy to you. And so whereas site energy is on-site energy demands. And so why is, for example, the site energy use drops so much when you electrify a home? Well, because at this point, then you're not accounting for the fuel it takes to generate the electricity. You're just getting the electricity. But you need, typically you need about, for every unit of energy you in combustion, so like natural gas, if you were to get 1 unit of natural gas and then use a natural gas generating facility turbine to convert that 1 unit of natural gas to electricity, by the time it gets to your house, how much energy is there left? Well, it's about like, it's between a quarter and a third. So let's just put it at 30%. So you lose, the 40 around, you lose around 70%. And a lot of that has to do with just the Carnot thermal efficiency limits of burning natural gas to be able to turn a turbine. That's something called the Carnot efficiency limit, and it's somewhere around like 0.4 something, I believe. And so even if you don't account for transmission losses and power conversion and stuff like that, from stepping up voltage, stepping down voltage and stuff like that, you're already losing about 60%, to heat. But then, you lose another, like, let's say like 10% through transmission and power conversion, then you're at 30%. So that's why this number is, so different in electricity scenarios. But then with natural gas, the idea is, well, the difference between these two numbers is not so big, because that natural gas is being burnt at your house, and so you're capturing 80% in the case of 80% AFUE furnace of that heat to go to your house, and therefore then you're not subject to that Carnot efficiency limits. But then at the same time, though, where the caveat is, when you burn natural gas, even you have a 98% AFUE, which is about the highest you can get, furnace or tankless water heater, you're at 98% efficient. That's great for natural gas, but with heat pumps, you can get, for every unit of energy you put in, you can get 3, 4, 5 units of heat or cooling out of a heat pump. And then even in the dead of winter, January, February, December, January, you're typically able to get 2.8 coefficient of performance. So for every unit of electricity you put in, you get 2.8, 3, 3.3 in dead of winter. And then when you start getting the shoulder season, then you're at like 4 or 5 COP easily. So that's why, even though if it takes, the efficiency of converting natural gas to electricity is not amazing, the fact that you gain back there and additionally some more with heat pumps, that's why heat pumps are so great. Wasn't the idea behind net metering that utilities would sell trade on this intergrid and other regions need to energy in the summer? Yes. So for a long time, electric grids are summer peaking. So as you can see, like, a little hump in like July. And so then solar also generates the most in July. And so then that helps manage that summer peak. that's great. But if we move to a scenario where, you know, people are switching natural gas furnaces to heat pumps, then we are transitioning to a winter peak. And the interesting thing about winter peaks is that they're much, much more peaky than any summer peak we've ever seen in the grid. So therefore, that creates a whole different scenario that needs to be looked at differently. And in that scenario, net metering will likely never make sense. Okay, so will the 30 kilowatt system cover needs on a day-to-day basis? Not always, because sometimes you get 3 days straight of sun, which is why in this economic analysis, there's $8,700 in batteries, and that's more than enough batteries to get you through, you know, a winter's night, and even enough storage to get you through, you know, 1 or 2 days of cloudy days in the winter. I mean, certainly there are, you know, times in the winter when you get like 7 days straight of cloud, but that's actually quite rare. If you look at the weather forecast and analyze it on an hour by hour or day-to-day basis, you find that like every time that there's a period of clouds, it breaks about like in 3 days and it gets sunny again for some period. That's much more common than the 7 or 10 days of straight clouds. Please discuss utility gas central installations versus having gas individual homes. So that's another interesting thing to discuss is the amount of natural gas or methane leakage in the distribution system. So distribution system meaning like, you know, through the neighborhood streets and stuff to your house. That leakage rate has not been really well characterized. So there's, you know, been people that have done really good analysis to estimate that leakage. But the consensus is that, you know, if we're on the middle to high part of that estimate, then the climate change effects of that methane is as bad as if we continue to burn coal in the electric generation side, rather than this whole like effort to switch from coal electricity generation to natural gas. So it's really bad that if we're on the high side. If we're on the low side, it's a little bit better. But then, you know, but if everybody switched to heat pumps, then that COP of 3 or better really puts us back into the electric category as being a clear winner. And then the other thing about natural gas is if we are not careful about natural gas, I'm sorry, if we're not careful about electrification and we just go from baseline home to just electrification, we get this huge winter peak in January and December in electricity demand. What a lot of scenarios have found is that the pipeline to these natural gas generating power plants is just not big enough. So even if they're running full bore, they can't get enough natural gas in order to, you know, supply the additional energy needed. So we have a bit of a pipe diameter problem for the electric utility in order to generate the huge amount of electricity needed in the scenario where you electrify but don't improve your building enclosure. But when you start improving your building enclosure, then that picture starts to it looks a lot better. Then the electric utilities are not running out of natural gas during the peak periods in December, January. And so that's also another like, okay, can you actually make this work like in reality type situation? And then, yeah, we chose September 9th to avoid Labor Day weekend. Okay, what do you think about future of hydrogen and hydrogen boilers? So the story about hydrogen is if you just burn it, the efficiency is really not that good. If you run it through a fuel cell, then the efficiency is like double than what the efficiency you'll get out of burning hydrogen. So if it's a hydrogen boiler, I would hope that it is a fuel cell boiler, but I've never heard of a hydrogen fuel cell boiler. I've only heard of burning hydrogen in a boiler, but as I said, like the efficiency of burning hydrogen is not very good. And then the production of hydrogen with electrolysis is also not very good. There's multiple efforts at the DOE to, create funding opportunities that there's a lot of money that the DOE is willing to give anybody who can figure out how to generate clean hydrogen more efficiently. But it's a matter of like, do you have that idea? Because I certainly don't have that idea. So I have not been able to pitch to that funding opportunity because I don't have an idea. And then American Medical Association health warnings about gas appliances due to leaks. Yes, that is a problem. But in addition to that, there's also a lot of papers specifically looking at the indoor air quality problems associated with burning natural gas in a stove. One is the emissions are really bad. Even if you run your gas, if you run your range hood, but what we also find is that, like, due to the fact that a lot of range hoods are quite noisy, a lot of people don't consistently operate their range hood. And then when you're cooking with natural gas and you're not operating your range hood, then the indoor air quality gets just insanely bad. And that's a problem. Okay, well, that's all the questions.
Thank you
We're a
so
little bit over
much,
time.
Edward. Yeah, we went over, but it was all super informative. And thanks everybody for coming. And look for that email with the recording coming out early next week.
Right. And then I look forward to giving the next Green Energy series about seasonal thermal energy storage.
Great. Thank you. See everybody later.
Okay, excellent.
Bye.